Hello everyone, I am Aryaman Maithani and I will be giving this talk with Manav on Betti tables of quadratic ideals in characteristic 2. So let us first start with some notations and basic definitions. So throughout this talk we will be walking over this polynomial ring over the field F2. By M we shall denote this homogeneous maximal ideal generated by all the variables. A polynomial is said to be homogeneous if each monomial appearing in it is of the same total degree. So this is what one is familiar with homogeneous polynomials. And an ideal is said to be homogeneous if it can be generated by homogeneous polynomials. So it has a generating set consisting of homogeneous polynomials. And we shall always be focusing on homogeneous ideals which are contained in M. A graded free resolution or simply a free resolution of an ideal I is a sequence of this form. So we have these free modules and these are linear maps between them such that each di satisfies this exactness condition and d naught is onto. So we are simply saying that this complex is exact. Moreover, the entries in any matrix representation of di must consist of homogeneous polynomials. And we say that a resolution is minimal if each entry is not just homogeneous, but it's actually in the homogeneous maximal ideal. So we don't have any units. And it can be verified that these definitions are independent of which matrix representation we pick. The ith, so this beta i's which were appearing earlier, those are called the Betti numbers. And the Betti number of an ideal is simply the Betti number of any of its minimal free resolution. So this is independent of whichever resolution we pick. The sequence of all these Betti numbers is denoted like this, and it is called the Betti sequence. And as will be the case for our ideals, that these will actually be finite sequences in the sense that they will be zero eventually. So we simply write them like this. And we define this order where we compare two Betti sequences by comparing individual entries. Moreover, we talk about something called graded resolution. So we had defined graded resolutions, but we also need to take care of something more, which are the degrees. So consider we have this free resolution of this ideal. And here our matrices have a degree 3, degree 2, and a degree 5 polynomial in the columns. So we keep track of this by denoting it in this form. So we have r minus 3, minus 2, minus 5. To denote the fact that after multiplication, we should get r without any degree. Similarly, here we have r minus 4 because this has degree minus 4. This has degree 1 to get degree minus 3. So looking at similarly in the second column, we have a 4 here and a 2 here. So eventually we should have minus 6 over here. So this is just to make sure that the degrees are compatible. And so then we get the graded Betti numbers, which is simply the number of copies of r minus j in the ith step of the resolution. So originally we had written r beta I, but each r beta I can decompose as copies of r minus j. So beta ij is simply the number of copies of r minus j in the ith step. And the Betti table is just a way of representing all these entries at once. So the jith entry, which is the jth row and ith column, that is defined to be beta I comma I plus j. So as an example, we had this earlier. So that's what we see is this. So we have one here, which is this one here. Then we have r minus 3, r minus 2, and r minus 5. So that is the minus 2th, minus 3th, and minus 5th entry. And similarly for r minus 4 and minus 6. And whenever there is a 0, whenever there is, for example, no r minus 4 over here, we just put a dot. And this row on top is giving us the Betti sequence. So this will be the sum of all the entries in that column. In this project, we are interested in looking at resolutions of quadratic homogeneous polynomials. And we do it in two such ways. So first, we assume that I is going to be an ideal of this form. And then this discussion is broken up in two parts. So the first is we use the computer algebra system called Macaulay 2 to generate the Betti tables. And secondly, we proved some results by general theory. Let us go on to the computational results. So when we have only two variables, then the Betti tables are quite easy to compute because of the small amount of ideals that we have. So there are only 7 such quadratic polynomials, 2 cubed minus 1. And in turn, that only gives us 127 generating sets. So look at all possible subsets of the 7 element set. Then we generated all of these ideals using Macaulay 2 and found out that even though we have so many possible generating sets, there are only 15 distinct ideals. And this corresponds to only 4 distinct Betti tables. So these are the 4 Betti tables which we get. The number after them represents the number of times that they were repeated. In 3 variables, the earlier approach will not work since there are 63 quadratics. So this ends up with a very big number of possible generating sets. So we do something different. Since we're not interested in just any ideal, we're interested in very particular forms of ideals. These ideals are actually in bijection with this vectors, with the subspaces of this vector space. So this is a vector subspace of the polynomial ring, and we look at its non-zero subspaces. So there are only 2,824 such subspaces. So there are only these many such ideals. Now we were able to compute them in Macaulay 2, and we get 15 distinct Betti tables. So we have depicted them on the next slides. So here are 6 and here are 9. One thing to notice is that the first Betti number will always be a 1 because we are just mapping R onto R mod I. And the second column will actually give us the number of generators which are needed to generate the ideal, the minimum number of generators. So we can see that there are 5 of them. So 1, 2, 3, and 2 more on the next slide, which require 3 generators and no fewer. After looking at these Betti tables, we can now fix the codimension. So given any ideal, it has a codimension, and we can look at the Betti tables corresponding to each codimension. So we get something called the hash diagram of these posets. So these are diagrammatically depicted, where if there is a line between two ideals, between two sequences, the one above it is greater than the one below. So this is a poset. So for example, these two sequences here are not comparable. And whenever there is comparable, we have a line between them. Now, before going on to the theoretical results, we see two key results which helped us. So the first is the Koszul complex. So before that, we just recall what a zero divisor is. So given a ring A, an element of A is said to be a zero divisor if it multiplies with a non-zero element to give you 0, and it is said to be a non-zero divisor otherwise. So now let us consider the ring R to be F2, the polynomial ring, and then we have elements in the homogeneous maximal ideals such that F1 is non-zero and Fi is a non-zero divisor in the quotient R mod F1 up until Fi minus 1. In this case, we get the minimal free resolution is of the following form. So we have this sequence, we have R n choose 1. These are the binomial coefficients on top up until R n choose n. And we have not depicted the maps, but in fact one explicitly knows the maps appearing as well. In turn, one can calculate the Betti table explicitly. Now we see what the mapping form is. So suppose that we are given an exact sequence of this form. As usual, i's are ideals. And suppose we are given minimal free resolutions of the left and the middle, I1 and I2. Then this map between them can be extended to a map of complexes. We'll see what this means in a minute. Furthermore, we can combine these two resolutions to give a free resolution of I3. And the important part to us is that this resolution is minimal if and only if the image of f dot is contained in m times g dot. And we are not so much interested in the maps because what we know is that once this condition is satisfied, then we can get the Betti table for I3 by appropriately adding the Betti tables for I1 and I2. And the way one does this is by shifting the Betti table of I1 appropriately and juxtaposing it on I2. And to see what we mean by the extension of maps, so we have a map from R mod I1 to R mod I2 as follows psi. And what I'm saying is that we have these maps phi naught, phi 1, phi 2, such that all of these squares commute. Moreover, the condition that the image of f dot is contained in phi times m times g dot is simply saying that each of these phi i's have matrix entries in the maximal ideal. And now we move on to the theoretical results.
Hello everyone, I am Manav Batavia and I'll be taking over for the rest of this talk. So now we talk about some theoretical results. Let us start with ideals with one generator. This is the simplest case. Indeed, given a non-zero f in the maximal ideal, which is x1 to x3, we simply have this resolution for R mod f. Thus, the Betti table of I, where I is principal, is given by this. We now move on to the case of ideals with two generators. Let us choose two non-zero elements in the maximal ideal, f1 and f2. We resolve I equal to f1, f2 by considering the following two cases. The first case is if f2 is a non-zero divisor in R mod f1. You might recall that this is the condition of the theorem on Koszul complexes which we had mentioned earlier. As a consequence, this is the resolution of R mod f1, f2. In particular, since f1 and f2 are quadratic, we get the Betti table as this. The second case which we have is if f2 is a non-zero divisor in R mod f1. In this case, defining gi as fi upon gcd of f1, f2 for I equal to 1 and 2, we get a minimal free resolution of f1, f2 as follows. In this case, since f1 and f2 are quadratic, we can compute that the Betti table is exactly this. So as a result, we have resolved all ideals with two generators, as there are only two cases. f2 is either a non-zero divisor in R mod f1 or a zero divisor in R mod f1. Moving on, we go to all ideals with three generators. To resolve all the quadratic ideals f1, f2, f3, we divide the ideals into four cases. The four cases over here are very similar to those in the two generator case. So over here we have case 1 is f2 is a non-zero divisor in R mod f1 and f3 is a non-zero divisor in R mod f1, f2. f2 is a zero divisor, f3 is a non-zero divisor in R mod f1, f2. f2 is a zero divisor, f3 is a zero divisor. And f2 is a non-zero divisor, f3 is a zero divisor. In all, there are 1,395 ideals with three generators in f2 of xyz. Let us come to the first case. The first case was where f2 is a non-zero divisor in R mod f1 and f3 was a non-zero divisor in R mod f1, f2. Once again, using the Koszul complex, we can conclude that the Betti table corresponding to R mod f1, f2 is precisely this right here. We counted 512 such ideals. An example of such an ideal is x square, y square, z square. Moving on to the next case. The next case is where f2 is a zero divisor and f3 is a non-zero divisor. Using the mapping phone and the fact that R mod f1, f2 has a Betti table of the form A, you might recall that this was one of the Betti tables in the case of two generators. We concluded that the Betti table corresponding to R mod f1, f2, f3 is of the form B. So this Betti table was obtained by appropriately adding Betti tables, as we had mentioned earlier. 297 such ideals, and here is an example of such an ideal: x square, xy, z square. For the next two cases, our strategy is to use the mapping cone again. We have the following short exact sequence: 0 going to R mod f1, f2 colon f3 minus 2 to R mod f1, f2 to R mod f1, f2, f3. This minus 2 once again is just to maintain the degree. So the map over here is multiplication by f3, and since f3 is a quadratic polynomial, to maintain the degree we must have minus 2 over here. Now let us consider minimal resolutions of f1, f2, f1, f2 colon f3 and f1, f2. Note that f2 is a zero divisor, f3 is a zero divisor over here. So as done in the two generator case, the resolution of R mod f1, f2 is precisely this: r minus 2 square, r minus 3, 0. Now we come to the resolution of R mod f1, f2 colon f3 of minus 2. Note that the first step must be r minus 2. The next step, in general, we can write any three module as r minus j power beta 1, j. for j greater than equal to 3. The question arises, why should j be greater than equal to 3? So that is because over here, as we see j is equal to 2, there is just one j and it is equal to 2. Note that this is a minimal resolution. If you recall, the definition of a minimal resolution involves the matrix entries all being in the maximal ideal. That means none of them can be degree 0 elements. Since all these matrix entries are at least of degree 1, the degree of this j must be minus j must be at least 1 less than minus 2. And hence j must be greater than equal to 3. Similarly, over here, all the matrix entries must be in the maximal ideal. So they must be of degree greater than 0. And for the same reason, the degree must decrease by at least 1 from minus 3 to at least it must be minus 4. Right? And then j must be greater than equal to 4. One important thing to note over here is that in this case, the degrees over here are mismatched. So over here, you cannot have minus 2. Over here, we have minus 2, but over here, none of these can have minus 2. This is j greater than equal to 3. Similarly, over here, we have minus 3, but none of these j's can be minus 3. This is important because this implies that the matrix of these maps, if you look at the matrix of these maps, then they cannot contain an element of degree 0. Because if they contain an element of degree 0, they wouldn't be able to go to minus 3. Like for example, we have an element in minus 4 over here. If we multiplied it by an element of degree 0, it wouldn't go to minus 3. That would be a contradiction. Hence, all the elements of these matrices must lie in the maximal ideal. And you might recall from the mapping cone theorem that this implies that the resolution which we get on adding the Betti table must be minimal. We will use that very crucially in what follows. So before we come to that, we prove that the colon ideal f1, f2, f3 is one of the following two types. Type 1 is it is principal and generated by a linear homogeneous polynomial. Type 2 is it is of the form g1, g2, where g1 and g2 are non-zero homogeneous linear polynomials, and g2 is a non-zero divisor in R mod g1. Thus, we have the Betti tables of the relevant ideals, and we can add them to complete the case. We get the following two possibilities for the Betti table of f1, f2, f3. This is in the case where f1, f2, colon f3 is principal, and this is in the case where f1, f2, colon f3 is of the form g1, g2, where, as you might recall, like from the previous slide, g2 is a non-zero divisor in R mod g. There are 161 such ideals. X square, x y, y square is an example of type A. X square, x y, xz is an example of type B. Now we come to case 4. Since f2 is a non-zero divisor, we now have resolutions of the form. So you might notice over here, since f2 is a non-zero divisor in R mod f1, over here R mod f1, f2 will have resolution R minus 2, R minus 2 square, R minus 4. So this is where we have something different from the previous case. Here is R minus 4, earlier it was R minus 3. Similarly, over here we have, as before, we are assuming that R minus 2 is obviously the first step, and after that we are taking the general case where we have R minus j, power beta 1, j, R minus j, beta 2, j. So this is the problem right here. Now that we have R minus 4 over here, j greater than equal to 4 might pose a problem, because if j is equal to 4, then the map over here could have elements of degree 0, and that is the problem for us. So to avoid this issue, we took a further subcategory. We took all ideals f1 such that f1, f2, colon f3 contains no linear polynomials. Note that if f1, f2, colon f3 contains no linear polynomials, j must be at least 4 over here, and since j is 4 over here, it must be at least 5 over here, since minus j must always decrease by 1. Once we have j at least 5 over here, once again we have a mismatch of degrees, and we can add Betti table to get a minimal free resolution of f1, f2, f3. This is how we do it. We split this case into two cases, as I just mentioned. f1, f2, colon f3 contains no linear polynomial. And in this case, we have that beta 1, 3 is 0 and beta 2, 4 is 0. This is just saying that j must be greater than equal to 3 and j must be greater than equal to 4 and j must be greater than equal to 5. As before, the mapping cone can minimally resolve the desired ideal. Note that from the earlier computational results, we noticed that there are 5 possible Betti tables for ideals with 3 generators. We were able to eliminate all the others to reduce that the Betti table in this case must be this right here, 1, 3, 4, 2. There are 336 such ideals. Then there's the second case where the colon ideal contains a linear polynomial. This case is unresolved. All in all, we have been able to resolve 1,306 of the 1,395 ideal to 3 generators. The remaining 89 follow this case. This work was done as a part of the Polymath Jr 2021 program. We'd like to thank our mentor, Dr. Alexandra Sachilanu, for guiding us. Thank you for attending this virtual talk.